Let us begin by understanding the topic of variation. Variation is natural. For example, the time it takes you to get to work. If you say that the time it takes you to get to work is 15 minutes, that means that 15 minutes is an average time over the last few weeks or months or years that you have been coming to the same place from your house. There may have been days when you have come to work in 12 minutes, 13 minutes, 15 minutes, 18 minutes, 17 minutes, but the average is always 15 minutes. Similarly, in injection molding or in any manufacturing process, you'll also see variation in the dimensions of the parts, in the part weights. In any of the inputs or outputs, there'll always be variation. For example, if you take 100 parts from the injection molding machine and weigh the parts, there has to be a variation in the part weights. For example, if you say all the part weights are 5.12 grams, and so you're going to conclude that there's no variation, that's not true, because if you take that decimal to the third digit, you are going to see the variation. So you'll have to go to 5.125, 5.127, 5.121. That is where you will see the variation. Why do we need to understand that variation? Here's another reason. Let's say that this is the nominal dimension you're trying to achieve. This is the lower spec limit and this is the upper spec limit. And this is the variation in the part quality that you have, but you have not measured it. But now, from this lot of material, from this lot of molded products, if you measure this part and conclude that all the parts are good and you ship it to the customer, it's very likely that the customer is going to measure this part here and he's going to say the parts are bad and he's probably going to want to send the parts back. That's the reason we need to understand the variation. In this case, both you are correct because you found a good part and he's correct because he found a bad part. But now these parts are not going to work for him because some of them are out of spec. That's the whole reason that you need to understand the variation. So what are the source of variations in the quality of a molded product? So for example, if I'm molding this part here, where does this variation come from? This variation can come from the machine. This variation can come from the environment. It can come from the personnel. It can come from the materials. It can come from the process. It can come from the measurement systems. And there are several other sources of variation. Each of these elements will have their own fishbone diagram and will induce variation within themselves. For example, the molding process. There are 11 plus 2 or 13 molding parameters on the molding machine that contribute to the molding process. A variation in each of these will induce variation in the final molding process. The aim should be to understand the source of variation and then to minimize it. It's impossible to eliminate variation from the molding process. If you look at the aim of a molding operation, you are trying to mold the parts consistently. You're trying to mold the parts that meet all the quality requirements, and you're trying to run an efficient process. There are three types of consistencies. The first one is a cavity to cavity consistency. That means I've got an 8 cavity mold, and if the length of the part is important, then the length of cavity 1 should be the same as length of cavity 2, should be the same as length of cavity 3, and so on. If I have all these cavities of the same length, then I say that I have achieved a cavity to cavity consistency. There are several reasons why we may not achieve cavity to cavity consistency. For example, if cavity 1 is not filling the same as cavity 3, or if the gate size in cavity 1 is bigger than the gate size of cavity 3, then this cavity is going to have a different dimension compared to this cavity. Or by mistake, the mold maker did not cut the steel in cavity 2 similar to the steel in the other cavities. The dimensions are different. That will also cause a cavity to cavity inconsistency. Then we have a short to short consistency. The mold opens, ejects a part out, closes, goes through the injection molding cycle, puts out another part. If this length is the same as this length is the same as the length of all the parts that are going to be coming out of that mold, then we say we have achieved a short to short consistency. There can be several reasons why we may not have short to short consistency. The biggest reason is having a leaking check ring. That means the check ring is worn out over time, and now the amount of plastic that's being injected inside the mold is not consistent from shot to shot, and now that is giving you issues from shot to shot, and that's causing you shot to shot variation. The third type of consistency is a run to run consistency. That means during every consecutive run, the molded parts have an identical quality as the previous runs. So we're molding connectors, we molded 100,000 connectors, and let's look at the length of the part again. There's going to be a certain average, a certain variation. Now you change the mold. Once you change the mold, let's say we start molding some spacers of a different material. So what do we do here? We completely change the molding process. That means all the times, temperatures, speeds, pressures, all the settings on the molding machines are now changed to mold the spacer mold. And once this run is done, if we change the mold back to the connector mold and mold another 100,000 parts, then if this average and this variation is the same as this average and this variation, then we say that you have achieved run-to-run consistency. However, the most important part of this run-to-run consistency is that the molding process that was used here in run number 1 should be the same as the molding process that was used in run number 2. So all the settings and the outputs, all the inputs and the outputs should be the same from run to run. And then we say we have achieved a run to run consistency. And this is one of the most challenging consistencies that every single company has issues with and has problems with. The last time the mold ran fine, but this time the mold had issues. And that's a standard line in most companies. And somewhere or the other, at some point or the other, that line always comes up. And the whole idea of developing a good, robust process is to get away from these inconsistencies and have achieved the 3 consistencies. Meeting quality requirements, of course, means that you must always be within spec. Running an efficient operation means optimize cycle times, reduce scrap at startup, 0 scrap during production. There'll always be some rejects at the startup depending upon your part quality requirements, depending on the material molding and several other factors. But during production, you should always have 0 scrap, and that's 100% possible. If you have a process that is like this, it's not acceptable, because out here, for some reason, the parts went out of spec. So now QA needs to be involved, a technician needs to be involved, there's time loss, material loss. Then somebody comes, changes it based on an opinion, because in the last job, because they changed cooling time, it worked, and now they started changing cooling time here, but it might be a very temporary fix. But the main reason why the problem existed to came up with in the first place out here is not known. And so without doing proper troubleshooting, they overcompensate for that, and now they make parts on the other side of the spec, and now they start having issues again, right? So this whole thing is an inefficient operation, and we should not have a process that looks like this. My philosophy for developing a molding process has been very simple. If you want to drive your car in cruise control mode, let's say at 80 miles an hour, which of the following roads will you prefer? Would you like to drive at the edge of a cliff, or would you like to have a nice wide freeway? The answer is obvious. Let's say it's a 4-hour journey. There's absolutely no way that you're going to be able to drive at the edge of this cliff, a road that looks like this, for 4 hours, because at some point you are unfortunately going to go off the cliff. And for that reason, we need to have a nice wide freeway where you can set it in cruise control, and any small variations here and there will be compensated for, and you'll still be within your lanes and you can have a nice comfortable drive. My goal is to always have a molding process that runs in cruise control. That means once you set your process, it should run. We should not be tweaking it constantly. Should not be changing processes constantly. It should not happen that the first shift has a different process than the second shift, and then the third shift has got his secret process down in the drawer. He takes it out and he's the only guy who can run this process. That should not happen. Those processes are not robust processes. For a process to have the three consistencies that we talked about and have the least amount of problems with least amount of tweaking, the processes must be robust, they must be repeatable, and they must be reproducible. All the three R's are extremely important. The main reason why we have all these issues with inconsistencies is the way the plastics shrink. So in injection molding, we take plastic, we melt it. When we melt it, the volume increases. Then you inject it inside a mold where the volume decreases because it cools down. This decrease in volume is called as shrinkage. But the problem is, this shrinkage is not easily predictable. This shrinkage is not the same in all the areas of the mold. In some parts and thicker sections, you'll have much higher shrinkage compared to the thinner sections. Every plastic has its own material shrinkage values and its own range. For example, if you look at POM or acetals, they are basically 1.7 to 2.3%. ABS 0.6 to 1.1%, right? So as a mold maker, it becomes very difficult to pick a number. And there are several parameters in the molding machine that can influence the shrinkage. So all these things will basically affect your shrinkage and cause the inconsistencies molding process. Let's talk about processing parameters having an influence on the shrinkage. Let's say that the quality department comes to you and says that the dimension of the part is below the lowest spec limit. What would one do as a processor? The possible solutions are reducing the mold temperatures, reducing the melt temperatures, increasing the packing pressure, increasing the holding time, increasing the cooling time. All these changes will affect the shrinkage and will increase the length of the part or the dimension of the part. But what is the right solution? You have to follow the principles of scientific molding, scientific processing, and that is what is going to give us the best solution based on data. All the changes in injection molding must be data driven. You must not change anything if you don't have data. Data is numbers. You must have data to make any changes in the molding machine. You must know what happens if you increase and decrease temperatures. What happens if you increase and decrease times? How much does the dimension change by? Unless you know that information, one should not be making any changes. You should make changes not based on opinion, but based on data. Scientific molding and scientific processing. Scientific molding is what is done at the molding machine, all the studies that one typically does at the molding machine, for example, viscosity curves, pressure drop studies, gauge seal studies. All these studies are scientific molding studies. However, I have been studying what happens to the plastic from when it enters the facility to when it leaves the facility as plastic part. Understanding the science behind this complete journey is what I call as scientific processing. Things like how much And how long do you dry the plastic? What happens if you overexpose the plastic to the temperatures and the times? What happens to the part after it comes out of the mold? That is post-mold shrinkage. How does the plastic dimensions change after it comes out of the mold? We know that, for example, polypropylene parts, after they mold it, 2 days later, the dimensions are different. That is basically post-mold shrinkage. Understanding the science behind post-mold shrinkage, understanding drying, all these terms come under scientific processing. Scientific processing and scientific molding, they are understanding the science behind molding, but it's very important that we also know that it is not blindly following a set of procedures. That's one of the reasons people fail in the implementation of scientific processing and scientific molding, because they go and blindly follow the set of procedures that were given to them during the seminar or a class or online, some of the resources that they've gone through. So please remember, it is not blindly following a set of procedures. To succeed in injection molding and to get a good quality part, there are always 5 elements that are important. The first one is a part design. You have to have a part design that will lend itself to injection molding. For example, you cannot have a part that's too thin. You can't have a part that's too long unless you have got multiple gates. A lot of part design principles that you have to follow. And plastic part design principles are different from metal part design principles. Then the plastic material. You have to choose the right plastic material in order to make sure that you're going to get the required properties and achieve the dimensions you're looking for. Mold design and the build is a third element. And this element is extremely important because you have to make sure that you have got a good mold designer who's going to design the mold based on the processability of the part. Putting the gates in the right location, putting the vents in the right location, putting enough vents. All these are very important and they must be taken into consideration, and you must have a good mold designer who does this. And the builder, the person who builds the mold. You have to have a good mold builder who's going to put the right size vents in there, who's going to be able to make sure that the shutoffs are good so that the parts do not flash under low pressure. Then the choice of the molding machine is extremely important. You cannot mold a small part in a very big machine because you can burn the plastic. If the residence time is too high, you can burn the plastic. And therefore, the choice of the molding machine is also important. And the last is the molding process. The molding process can only be as good as the rest of the 4 elements. If you have issues with the quality of these 4 elements, then your processes are not going to be robust. The process is not going to be consistent. And you're going to have issues and you'll be constantly tweaking the process, and you're going to be running the process right at the edge of the cliff. It's like a relay race. You may have the world's fastest person in the front, right? But at the back, if you don't have a good runner, then you're never going to win the race. So you are only going to get good quality parts when all these 5 elements are optimized. Since all the 5 elements are important, you should never have an over-the-wall engineering approach in your company. You should make sure that whenever you get a new project, all the bright people are pulled onto one table where they discuss the molding project and understand each other's role in there, and that is what is called as concurrent engineering. And concurrent engineering is very important for the success of a molded product. That was an introduction to scientific molding and scientific processing. At the end of this series of seminars, the attendees is going to be able to learn how to develop a good, robust molding process. We will introduce some basics about part designs, materials, mold designs, the selection of molding machines, so that one understands how that is applied to the molding process and how important each of those elements are to make sure that the process is robust. The Lego company, it seems like, molds a very simple product. However, They have taken into consideration all these 5 elements, and therefore they are one of the most successful molders out there today. You can take a Lego that is molded in any part of the world, made in Europe, made in China, made in Mexico, and put them together, and they will fit exactly the same as they would from the same lot of molded products. The quality here is very important because if it's too tight, a kid is not going to be able to push the Lego blocks together, and if they're too loose, then the Lego blocks will fall apart. And therefore, they're extremely tight tolerance molding parts, and all the 3 consistencies that we talked about, cavity to cavity, shot to shot, and run to run consistencies are extremely important in such cases. In the following series of videos, we will be discussing all the molding parameters on the machines and how to make each of the settings for each of these parameters robust. I call them the 11 plus 2 molding parameters. The reason I say 11 plus 2 and not 13 is because sometimes the pack and hold are combined into one phase and is called as the pack and hold phase or simply as the holding phase. In no particular order of importance, the inputs are the cooling time, packing pressure, packing time, melt temperature, injection pressure, injection speed, back pressure, screw rotation speed, the shot size, the transfer, the mold temperature, the holding pressure, and the holding time if they're split into 2. One must realize that in different parts of the world, the terminologies are different. In some cases, shot size is called as dosage. In some cases, the transfer position is called as a cutoff position. However, it's important that we understand what these settings are and what each of these settings do. These are all the inputs. At the same time, there are outputs. There are 8 outputs that are important: the actual melt temperature, the actual mold temperature, the injection fill time, the peak injection pressure, the pressure transfer, the cushion values, screw rotation times, and the cycle times. Inputs are what you're going to set at the molding machine, whereas outputs are a resultant of the inputs. There's one more input that is called as decompression that I do not consider as a setting on the molding machine, and that is going to become evident as we go through the class. It is an important setting, but we will discuss why it is not considered as one of the injection molding parameters. The philosophy of my mold qualification and process development is actually a 2-part process. The first part is the mold function qualification, and the second part is the mold quality qualification. In the mold function qualification, also called as a scientific processing section, this is where I explore the molding process. If you are a molder and you mold parts at a machine and you take it to your quality department, what is the first thing that the quality inspector is going to do? They are going to inspect the part first visually. They're going to look at the part and say, well, this part is not acceptable because it has got flash. This part is not acceptable because it has got sink. So the first line of inspection is a visual inspection. And for me, that visual inspection is very important because that defines the width of the freeway that we talked about earlier. We must know what is the range of each of the 11 plus 2 parameters where we can mold parts that are cosmetically acceptable. Those are known as process windows. If the process windows are large, then we can guarantee having a good, robust process. It's very important to understand that we must not look at any dimensions during this stage. First, we need to find out what is the width of the freeway. And once we know what the width of the freeway is and where the dimensions are, Then we basically bring in the process into a robust area, check the dimensions and make the required adjustments in the steel and or in the product specifications. But if we start now modifying the process to meet the dimensions, we could now be at the edge of the cliff and we could fall off the process. Where are we as far as dimensions go? That is where we come into step number 2, which is the mold part qualification, also called as the design of experiment section. This is where we are going to test the effect of the process parameters on the dimensions of the part. This is where we're going to test how wide the dimensional process window is compared to the cosmetic process window that we achieved in the scientific processing section. Design of experiments must be done only after the cosmetic process window studies are done, because unless we know what the high and the low limits of the molding process are in a cosmetic manner, we will not be able to set the highs and lows for our experiments in the design of experiment section. So 2 parts. This is the flow chart. It's a very simple flow chart. The first part is the scientific processing section where we do all the scientific molding studies. We do the melt preparation studies. And then the second part is where we look at dimensions. A brief syllabus of what we are going to cover in the next few lectures. Polymers and plastics would be the next topic. We have already covered the topic of introduction to scientific processing. We'll next talk about polymers and plastics. We'll then talk about injection molding machines and machine selection. Injection molding process. What is it? What are each of the different molding parameters? What are the 11+2 molding process parameters? Process development, the 6-step study. Process development, design of experiments. We'll talk about some troubleshooting and some defects and a quick plan how to get started at your location. It's very important to know that the goal of this seminar is to understand the science of injection molding and apply the knowledge to establish a robust process and troubleshoot when necessary. It's all about the basics. Until you have the basics firm, until you have clear concepts, you're not going to be able to come up with a good robust process.